Hello, biology students, and welcome back to another text audio edition of our text. Today we are going to be starting our biochem unit, so as always, we're going to be delving into our text a little bit. And our first section of our text is going to be called The Nature of Matter. All right, so let's go ahead and get started. And while you're watching this, please complete that companion reading guide, that's section 2.1 reading guide. Okay. Life depends on chemistry. When you eat food or inhale oxygen, your body uses these materials in chemical reactions that keep you alive. Just as buildings are made from bricks, steel, glass, and wood, living things are made from chemical compounds. If the first task of an architect is to understand building materials, then the first job of a biologist is to understand the chemistry of life. Atoms. The study of chemistry begins with the basic unit of matter, the atom. The Greek word atomos, which means unable to be cut, was first used to refer to matter by the Greek philosopher Democritus nearly 2,500 years ago. Democritus asked a simple question. If you take an object like a stick of chalk and break it in half, are both halves still chalk? The answer, of course, is yes. But what happens if you go on? Suppose you break it in half again, and again, and again. Can you continue to divide without limit? Or does there come a point at which you cannot divide the fragment of chalk without changing it into something else? Democritus thought there had to be a limit. He called the smallest fragment the atom, a name scientists still use today. Atoms are incredibly small. Placed side by side, 100 million atoms would make a row only about 1 centimeter long, about the width of your little finger. Despite its extremely small size, an atom contains subatomic particles that are even smaller. Figure 2.1 shows the subatomic particles in a helium atom. The subatomic particles that make up atoms are protons, neutrons, and electrons. Protons and neutrons have about the same mass. However, protons are positively charged particles, and neutrons carry no charge. Their name is a reminder that they are neutral particles. Strong forces bind protons and neutrons together to form the nucleus, which is at the center of the atom. The electron is a negatively charged particle with 1 divided by 1840, the mass of a proton. 1 almost 2,000th the mass of a proton. Electrons are in constant motion in the space surrounding the nucleus. They are attracted to the positively charged nucleus, but remain outside the nucleus because of the energy of their motion. Because atoms have equal numbers of electrons and protons, and because these subatomic particles have equal but opposite charges, atoms are neutral. Figure 2.1. Helium atoms contain protons, neutrons, and electrons. The positively charged protons and uncharged neutrons are bound together in the dense nucleus, while the negatively charged electrons move in the space. Elements and isotopes. A chemical element is a pure substance that consists entirely of one type of atom. More than 100 elements are known, but only about 24 are commonly found in living organisms. Elements are represented by a 1 or 2 letter symbol. C, for example, stands for carbon, H for hydrogen, and Na for sodium. The number of protons in an atom of an element is the element's atomic number. Carbon's atomic number is 6, meaning that each atom of carbon has 6 protons and consequently 6 electrons. See Appendix G, the periodic table, which shows the elements. Isotopes. Atoms of an element can have different numbers of neutrons. For example, some atoms of carbon have 6 neutrons, some have 7, and a few even have 8. Atoms of the same element that differ in the number of neutrons they contain are known as isotopes. The sum of the protons and neutrons in the nucleus of an atom is called its mass number. Isotopes are identified by their mass numbers. Figure 2.2 shows the subatomic composition of carbon-12, carbon-13, and carbon-14 atoms. The weighted average of the masses of an element's isotopes is called its atomic mass. Weighted means that the abundance of each isotope in nature is considered when the average is calculated. Because they have the same number of electrons, all isotopes of an element have the same chemical properties. Radioactive isotopes. Some isotopes are radioactive, meaning that their nuclei are unstable and break down at a constant rate over time. The radiation these isotopes give off can be dangerous, but radioactive isotopes have a number of important scientific and practical uses. Geologists can determine the ages of rocks and fossils by analyzing the isotopes found in them. Radiation from certain isotopes can be used to treat cancer and to kill bacteria that cause food to spoil. Radioactive isotopes can also be used as labels or tracers to follow the movements of substances within organisms. Figure 2.2. Because they have the same number of electrons, these isotopes of carbon have the same chemical properties. The difference among the isotopes is their number of neutrons in their nuclei. Chemical compounds. In nature, most elements are found combined with other elements in compounds. A chemical compound is a substance formed by the chemical combination of two or more elements in definite proportions. Scientists show the composition of compounds by a kind of shorthand known as a chemical formula. Water, which contains two atoms of hydrogen for each atom of oxygen, has the chemical formula H2O. The formula for table salt, NaCl, indicates that the elements from which table salt forms, sodium and chlorine, combine in a 1-to-1 ratio. The physical and chemical properties of a compound are usually very different from those of the elements from which it is formed. For example, hydrogen and oxygen, which are gases at room temperature, can combine explosively and form liquid water. Sodium is a silver-colored metal that is soft enough to cut with a knife. It reacts explosively with cold water. Chlorine is very reactive too. It is a poisonous greenish gas that was used to kill many soldiers in World War I. Sodium and chlorine combine to form sodium chloride, or table salt. Sodium chloride is a white solid that dissolves easily in water. As you know, sodium chloride is not poisonous. In fact, it is essential for the survival of most living things. Figure 2.3. The chemical bond in which electrons are transferred from one atom to another is called an ionic bond. The compound sodium chloride forms when sodium loses its valence electron to chlorine. Chemical bonds. The atoms in compounds are held together by chemical bonds. Much of chemistry is devoted to understanding how and when chemical bonds form. Bond formation involves the electrons that surround each atomic nucleus. The electrons that are available to form bonds are called valence electrons. The main types of chemical bonds are ionic bonds and covalent bonds. Ionic bonds. An ionic bond is formed when one or more electrons are transferred from one atom to another. Recall that atoms are electrically neutral because they have equal numbers of protons and electrons. An atom that loses electrons has a positive charge. An atom that gains electrons has a negative charge. These positively and negatively charged atoms are known as ions. Figure 2.3 shows how ionic bonds form between sodium and chlorine in table salt. A sodium atom easily loses its one valence electron and becomes a sodium ion. A chlorine atom easily gains an electron and becomes a chloride ion. In a salt crystal, there are trillions of sodium and chloride ions. These oppositely charged ions have a strong attraction. The attraction between oppositely charged ions is an ionic bond. Covalent bonds. Sometimes electrons are shared by atoms instead of being transferred. What does it mean to share electrons? It means that the moving electrons actually travel in the orbitals of both atoms. A covalent bond forms when electrons are shared between atoms. When the atoms share two electrons, the bond is called a single covalent bond. Sometimes the atoms share four electrons and form a double bond. In a few cases, atoms can share six electrons and form a triple bond. The structure that results when atoms are joined together by covalent bonds is called a molecule. The molecule is the smallest unit of most compounds. The diagram of a water molecule in figure 2.4 shows that each hydrogen atom forms a single covalent bond with the oxygen atom. Figure 2.4. The chemical bond in which electrons are shared between atoms is called a covalent bond. In a water molecule, each hydrogen atom shares two electrons with the oxygen atom. Van der Waals forces. Because of their structures, atoms of different elements do not all have the same ability to attract electrons. Some atoms have a stronger attraction for electrons than do other atoms. Therefore, when the atoms in a covalent bond share electrons, the sharing is not always equal. Even when the sharing is equal, the rapid movement of electrons can create regions on a molecule that have a tiny positive or negative charge. When molecules are close together, a slight attraction can develop between the oppositely charged regions of nearby molecules. Chemists call such intermolecular forces of attraction van der Waals forces, after the scientist who discovered them. Although van der Waals forces are not as strong as ionic bonds or covalent bonds, they can hold molecules together, especially when the molecules are large. People who keep geckos as pets have already seen van der Waals forces in action. These remarkable little lizards can climb up vertical surfaces, even smooth glass walls, and then hang on by a single toe despite the pull of gravity. How do they do it, you may ask? No, they do not have some sort of glue on their feet, and they don't have suction cups. A gecko foot, like the one shown in figure 2.5, is covered by as many as 500,000 tiny hair-like projections. Each projection is further divided into hundreds of tiny flat-surfaced fibers. This design allows the gecko's foot to come in contact with an extremely large area of the wall at the molecular level. Van der Waals forces form between molecules on the surface of the gecko's foot and molecules on the surface of the wall. The combined strength of all the van der Waals forces allows the gecko to balance the pull of gravity. When the gecko needs to move its foot, it peels the foot off at an angle and reattaches it at another location on the wall. All right, everyone, this wraps up our first section of our biochemistry text. Please complete that reading guide and have a wonderful day.